All right, let's take a look at your review sheet. So the way this works is I kind of march through each term. So the first term we covered in part two. Part two is our solar system. I want you to know generally there are two types of planets. And up here in the upper left-hand corner in red, I have terrestrial or Jovian. Jovian, of course, that corresponds to rocky or gaseous. And then I talked about the mnemonic device here, MVEM, JSUN. And remember, that's my very educated mother just served us, and somebody said nothing. I agree. I like that. Okay, so the order of the planets. And, oh yeah, and then I'm going to have a section there. It says pick out from photo. I'm going to actually have a little photo part of your test where I'm going to show you a picture of the planet, and you have to tell me which one it is. So there are 8 planets that you need to be able to pick out in a lineup. The next one, Kepler's 3 laws of motion, planetary motion. So be kind of familiar with what they are and be able to kind of explain them. The first one is the shape of the orbits with the sun at the one foci. Remember, the sun is kind of offset, so we have perihelion and aphelion. And then the next one, planets move fastest when they are at perihelion. That's his second law. Do I have his third law? Yes. Third law is that the further the planet is from the sun, like is it Jupiter far away or is it Mars closer in? Jupiter actually moves more slowly in its orbit than Mars. So that's that one. Let's see. And this one actually, I have 2 there. Let me go ahead and grab a pen here. So the solar cycle is 11 years, and you don't have to know much more about that, but it's 11 years. Remember, its activity ramps up, and then it calms down. That ramps up. And then this right up here, the sun's layers, okay, I have 6 here, and I guess that's the only hint I've got for you. There should be 6 in the atmosphere, and then 6 kind of in the inner part of the sun. So know those. Planets with moons and rings. I have in purple, all Jovians have rings and moons. So like Jupiter, Saturn, Uranus, Neptune. I mean, they all have rings. We think of Saturn as having rings, but actually its buddy Jupiter and the 2 blue guys, they have rings too, and of course they all have moons. In blue I have up there with regard to moons, the Earth has a beautiful moon, and the only other rocky planet, terrestrial planet to have moons would be Mars, and they're kind of ugly looking. Why is Mars red? That's rust, iron oxide. The next one, just know that of kind of features of planets, Jupiter's got a couple of cool ones. Jupiter actually has those Galilean moons that you can see through. I don't think you can see them through binoculars. I think Joshua asked that, can you see Galilean moons through binoculars? But you can see Galilean moons through the telescope. And you can also, hard to pick out through the telescope, but see Jupiter's great red spot. And the 2 blue guys, Uranus and Neptune, what makes them blue is actually methane in their atmosphere. Pluto's new classification, you should be proud of it, is a dwarf planet. What causes meteor showers? The Earth is passing through debris that was left by a comet. It just so happens that that debris was left in Earth's orbital path. So remember, comets, as they get close to the sun, they kind of start to break up, and that's kind of what the comet debris is all about. Speaking of comets, as they get close to the sun, they start to kind of flare up, kind of ionize, fall apart, and the tail is always blown away from the sun due to solar wind. Let's see, planets. Oh yeah, I think I just say, are there other those other stars that we see in the nighttime sky? Is it possible that they also have planets in orbit about them? And the answer is yes. Okay. On to, in a section I did part 1 and part 3. So lines of longitude. Lines of longitude I kind of have in green here. It's kind of going up and down. Lines of latitude, of course, going around the equator. So where do these lines begin? Well, with regard to latitude, they begin at the equator, and they go, which is 0 degrees, and they go to the poles, 90 degrees north, 90 degrees south latitude. And with regard to longitude, I have it in blue up here. They begin at the prime meridian. Remember, that's 0 longitude, and they go east and west, and they meet at the international date line, which is 180 degrees on the other side. Let's see. Oh, also I have in blue up here 5 named lines of latitude. So know the equator is 0, and then know our Tropic of Cancer is 23.5 degrees north, and Tropic of Capricorn is 23.5 degrees south. And then also know the circles. We have the Arctic Circle, which is 66.5 degrees north, and the Antarctic Circle, which is 66.5 degrees south. The direction of the Earth's rotation in orbit, even though I've got it wrong on my slides sometimes, I fight it, it's about counterclockwise. So the Earth spins on its axis counterclockwise, and it orbits the Sun counterclockwise as you're looking down at the North Pole. The plane of the ecliptic is kind of like the frisbee that the path that the Earth orbits the Sun and all the other planets. General reasons for that the Earth has seasons, that's actually because the Earth's axis of rotation is tilted. The next one, general dates of the solstices and equinoxes in the Northern Hemisphere. Just kind of think of them as 3 months apart. So we have something happening in December, March, June, and September. If you just put 21st to the 23rd, I'm cool with that. So hopefully you know that in December we have the winter solstice, and then in March we have the spring equinox, and then in June we have the summer solstice, and then in September we have the fall equinox. Precession of Earth's axis of rotation. So that's that wobble that Earth's axis of rotation stays tilted about 23.5 degrees, but it will point to a different star, and that cycle's about 26,000 years. So no worries about Polaris not being our North Star. So regolith is like the soil on the Earth's moon, on Earth's moon, soil on the moon. By the way, I don't think I mentioned it, but the Earth's moon, we do a capital M-O-O-N, and like if it's a moon in orbit about another planet, we do a lowercase m. Let's see. Mare are the dark regions, yes, on the moon, and they are like plains. Mare and plains are the same thing. And then we have the highlands, which would be the light regions, and they're older, and Mare are younger. So the thing that causes Earth's tides is actually the gravitational pull of the moon, and sometimes we talked about how the sun can actually get involved in kind of giving a tug. So the sun gets involved and gives a tug when we have neap tides and spring tides. Now, spring tides are when things spring up, so actually the Earth's tides are kind of being extra pulled up, and that happens when the sun is aligned with the moon at either the new moon phase or the full moon phase. And then in neap tides, we have the sun working at a 90-degree angle to the moon. So that would be at first or third quarter. And then we talked about eclipses, and we talked about this umbral part of a shadow. So the umbral part of a shadow, whether it's the Earth's shadow or the moon's shadow, is the darkest part of the shadow. And eclipses. So generally know the diagram of an eclipse, and I've kind of put them on this review sheet. And also know then if you diagram the eclipse, you're going to see that actually solar eclipses, hiding of the sun, can only happen when the moon is in its new phase, and a lunar eclipse can only happen when the moon is in its full phase. And then we're on to the last part. Nope. Yes, maybe. So celestial sphere is kind of it's a model. It's basically saying that the Earth is in the center of things, and things kind of are stuck onto the celestial sphere, and the Earth kind of rotates. Now, is that the case? No, but does it kind of fit our observations? Not bad. So that's the celestial sphere. And astronomers find things on the celestial sphere, kind of like we do GPS, longitude and latitude, except it's called right ascension for equaling longitude on the celestial sphere, and declination equaling latitude. And then I have your favorite constellation. So there's a place on the test for you basically to tell me, kind of diagram your favorite constellation. Now, you could, even though the Big Dipper is not a constellation, it's a subgroup of a constellation called Big Bear or Ursa Major, but you can do the Big Dipper if you want to. So just kind of be able to do your best and kind of draw your favorite constellation. So then we talked about we need to use a distance of a light year to say how far away stars are and other galaxies and the edge of the universe in terms of light years away. So light year is the distance that light will travel in 1 year. And it seems like it's a far way away, and it is. Stars, like our sun, all stars actually create in their, they create energy in their cores via nuclear fusion. And it's not always this hydrogen plus hydrogen goes to form helium, but that's what's happening in the main sequence stars. We talked about main sequence stars. Then we talked about how do you say how bright an object is, and we said we talked about the apparent brightness scale, and I think that's the one I'm going to hold you to instead of even kind of the absolute brightness scale. But apparent brightness, remember, the dude kind of, I think, got it mixed up, I don't know. But a +1 is brighter than a +6, basically. So no, and so here I've got written down a -5 would be very bright, and a +5 would be very dim. And then we talked about how do you classify stars based upon their lines, their electron patterns, their stellar spectra. And that's where I said, oh, be a fine guy or girl, kiss me. O, B, A, F, G, K, M are the 7 types, what's called spectral types of stars. O is the hottest, and M is the coolest, and G is our sun, heart. And then we talked about the different stages in the life cycle of a star. And the main sequence stage is the first stage that a star turns on. And actually stars spend, whether they're massive stars living their lives quickly or light stars living their lives very slowly, they will spend most time as a main sequence star. They are actually fusing hydrogen in their core, and that's what our sun's doing. Then we talked about stages that a star goes through, and we said that low mass stars like our sun actually become giants, and then they kind of move over, they kind of slough off their material, and as they're going out, basically gravity loses out control of their outer edges, and they form these kind of cool cocoon-looking things called planetary nebula. That is so cool. And then we said that massive stars will actually not go out nicely like that. Massive stars, more than 8 times the mass of our sun, will actually go supernova. And one type of remnant left after supernova is called a neutron star. And remember, we talked about how neutron stars make these pulsar signals. Neutron stars, like a neutron soup sort of thing. Supernova, these are kind of out of order. Supernova is when a massive star ends its life with a bang. And then we go on to the last. Approximate age of the universe, and again, I think now it's up to like 13.8. I'm not sure, 13.75 billion years old. But I put 13.5 billion years old, I think, on your test. Generally know kind of the, I think you're supposed to diagram the Milky Way is one of your homework questions, I'm thinking. But generally know it's like 100,000 light years side to side, about 2,000 light years thick, has a nuclear bulge in the center. Also in the center is Sagittarius A star, the supermassive black hole, all of that sort of stuff. General types of galaxies. There are spiral galaxies, barred spiral galaxies, elliptical galaxies, and I don't have here irregular galaxies, but there are. See, distributions of galaxies across the universe. So that's where we kind of had these sort of kind of void areas where there are no clusters. Well, I guess I should start by saying that galaxies are grouped in clusters, and these clusters of galaxies are further grouped into superclusters, and they are kind of on kind of these filament sort of things around void regions. And actually, we think that kind of the overall structure of our universe with galaxy clusters and superclusters like that is directly related to the presence of dark matter. So what makes dark matter dark matter? Well, we can see its gravitational influence, but we can't see it. Okay, so it's under luminous. Let's see, dark matter. Yep, I think that's it.